So next example, right? Here's a ball, and then there's that here,
What page are you on, Professor?
116.
Thank you.
I'm gonna have something like this. And it's gonna be point O. And there's a force of 400 Newton. Like that. Angle of 30. One four, 6. Meter. So if you have something like that, so how much is going to be the moment about that point O there? So as I said, if I want to use the moment equation itself, that's the force times d, the thing is that I have to go ahead and extend that and find the d, and this is it, f times d. If I want to do it using the equation, and use f d. But it's doable. It's not nothing not doable. But finding that d is not straightforward is going to probably cause you a headache. So it says that instead of doing that, we can go ahead and find the component of that force, and then find the moment for the components, and then add them together. So if I have that force component, so you're going to have the horizontal component and the vertical component. So the horizontal component is going to be 400 sine 30, and the vertical component is going to be 400 cosine 30, because it's next to the 30, so it's going to cosine away from 30, so it is sine. Agree? So now, instead of doing it this way, instead of using that f equals d, I'm going to say, okay, m is sigma ft. And I have to consider the positive direction, so the positive rotation would be, assume counterclockwise positive. So, if I want to do that, then m is equal to, first I will start with the horizontal one. So the force is 400 sine 30. How much is the d?
Yeah.
So the d is the normal distance from it, so I can slide it from here to here. So the distance is point. That's going to be point. Is it positive or negative?
In this case, it doesn't matter to you, positive.
It does not. So if I bring this here, compared to the O, does it rotate clockwise or counterclockwise?
Oh, there. So yeah, be counterclockwise. So it's just positive.
So it's going to be positive. Then I will do the 400. It's gonna be 400 cosine 30, and the d for that 400 cosine 30,
0.4.
0.4. So it's the normal distance. Again, I can move it up here, and the normal distance between the point and that is 0.4. So it's going to 0.4.
Would that be a negative 0.4?
That's my next question. So if I hold bring it here, clockwise or counterclockwise?
Clockwise.
Clockwise. So it's going to be negative. So I will put the minus. So then m about 0.0 will be add them together. If I write it correctly, it should make it 98.6.
Do you want me to plug it in or just work it?
You can check it to make sure that we write it correctly. If I write it correctly, it should come out at 98.6 negative.
Yeah.
So, again, just remember, it's much easier that you want to calculate the moment about any point. It's much easier to find this component on the x and y axis, and then go ahead and try to find the moment for that point.
So if we were to try and plot this moment, is it just that angle that we started off with? That's what the moment, like that's what the vector of the moment would be? Is moment vector, or is that a scalar?
It's a moment, but if you want to draw it, you said your forefinger direction of the rotation, so it is negative.
Yep.
It is rotating
Clockwise.
clockwise, so it's going to be like that, and the moment would be
Into
into the board. So you have, you want to, for example, you want to draw it here, so it's going to be something like this into the board. But usually when you're when you're in 2D, usually you just say clockwise or counterclockwise as a magnitude shift. Rotate like that or rotate like that. In 3D, then we show the axis. You get so similar to this one. The next problem is that if I have again the wall and zero, something like this, going off the wall, and then I have a force. This is 5 kilonewton. Then it's 45 degrees here. And 30 degrees here. Force is 35 degrees.
What is that angle measuring?
So again,
That the 75 degrees. What is that measuring?
angle from here to here.
Okay.
It's not like off the line of action.
Yeah.
Yes. If you extend the line of action, that's 75 degrees. And this length is 3 meters. So if there's a point over here, want to calculate the moment of that force, the 5 kilonewton about that point.
I think we both have it. Okay.
So, okay, so if you have a problem like that, what we're going to find first, the force component in the y direction and the x direction. So y direction is going to be 5 kilonewton times sine 45, and this one's going to be 5 times sine 40. So then I'm going to write m is sigma b, assuming counterclockwise positive. So let's start from the x, so it's going to be 5,000 sine 45 times the distance, so this is the force. The distance for this one, the normal distance for this one, that if I have it, slide it here, that's going to be the distance, normal distance. So I need this distance here. So if I slide it here, that's going to be the distance, which is going to be, if this is a 3, how much is this? 3 sine 30?
Yeah.
So it's going to be times 3 sine 30. And is it positive or negative? Counterclockwise or clockwise?
Clockwise.
So if I slide it here, about O, it's going to be clockwise, so it's going to be negative. The next one, the force is 5,000 sine 45. The normal, the normal distance from here to here, that's the normal distance. So I need to find this distance, which is going to be 3 cosine 30. It's going to be 3 cosine 30. And if I have a force here about this one, it's going to rotate counterclockwise. So it's going to be positive. And if I write it correctly, so it should come out as 14.5 times 3 Newton meter.
Okay. I typed it in wrong, but it got the correct answer. Again.
It's a clockwise. It's a clock. So that's going to be, both of them are going to be negative.
Yeah.
Negative.
Yeah. So.
Both of them are going to be clockwise. So any question about this? Any of these two? So next we're going to start to look at it. So this is 2D, let's see. And relatively, if it's a 2D, that's how we're going to do it. Any force you have it, just find the component, find the moment for each component, add them together. That's how we are going to do it in 2D. Now let's look at it how we are going to do it in 3D. So remember, like the force, when we talk about it in 2D and 3D, usually says if you're in 2D, it's easier to work it as a scalar. If it's in 3D, it's easier to work it as a vector. So as a vector, so it's the same thing here for the moment. So the first thing that we're going to look at is the cross. So what was the dot product? So we have the dot product earlier, and so if I have two vectors that's going like so this thing, A, B, and there's gonna be theta. The dot product of the AB was the magnitude of the first one, the magnitude of the second one, and the cosine between them. So what's up? So dot product. But A dot B was A, B, cosine theta. That's one way that we could have writing it, or the component AX, BX plus AY, BY plus AZ and BZ. That's how we could write the dot product. So dot product, and it is the scalar. Magnitude of that, whatever you're going to get out of it, be a scalar. The cross product is going to be vector. What you're going to get. The magnitude of the cross product, so this will get it. It's going to be A, B. This time instead of cosine, it's going to be sine theta. That's the magnitude of that. So, if A the actual cross product will give you the C. It's going to be a vector. And that vector is going to be the magnitude of the C times UC. So the C will be the magnitude of the C and the unit vector along the C. This is the magnitude of the C, which is going to be A, B, sine theta, and unit vector along the C. And as before, we had it the unit vector along any vector is vector divided by its magnitude. That's it. Unit vector.
What's the difference between vector C and non-vector C? So I guess scalars.
It's just magnitude of in some of the book, for example, if this is a vector C, they show the magnitude like this. In this book, if it's a vector, they show the magnitude like that for some reason. So this is a vector. The direction of the A times B. Yeah, it's like A cross B. So if I have A, like the one I have here, and let's put it A, B, where would be the C?
Would it be the resultant vector?
Say it again.
So would it be the resultant, so like the middle of the two? So like what we were just doing, where you add everything up and you find the middle of the thing.
Yes, and more. So the thing is that if I have like that A and B, and if it's the A and B, C is gonna be perpendicular to the A and B.
Oh.
So it's always like X, Y, Z. So if you have the X and Y, it's gonna be Z. So it's always like that. Now, which direction is gonna be? We use the right hand rule. Put your forefinger in the direction of the first vector. Carry it toward the second one. Your thumb gives you the C. So, if I go from the A toward B, I'll be like that. In 2D, I cannot draw it like that, so I'm assuming I draw it like this. So, it's going to be the C perpendicular to both of them. If I change it, instead of that, if I have it, I'll change it. So, if I have A, B. So this is the A cross B. What happened here? Or let's not. Let's do it the other way. It's easier to understand. Let's have it as the A and B. But let's say so. This time B cross A. What would be B cross A?
Would it just be going the opposite direction? So instead of having your C point up, it almost be pointing down.
So, correct. So this is the first vector, is the B. So you put forefinger in the direction of the B, carry it to the second one, which is going to be the A. So your thumb would show us, so it's going down. So it's going to be cross A. So unlike this one, A cross B is negative of the B cross A. So remember that there are always, no matter how is the A and B, the C, if this is the A and B, C is perpendicular. If this is the A and B, it's still going to be perpendicular. If this is the A and B, it's still going to be perpendicular.
So that'd be, as long as A and B are on the same plane, then C is perpendicular to them.
There are two lines that can always pass the plane
Oh,
from there.
yeah, okay.
So we can so that's going to be always perpendicular to the plane that passes through the two lines. Got it? So for like the next part, so the cross vector of the cross product of the unit vector. So I cross J, I cross J would be K. J cross K would be I. And K cross I would be J. I, J, J, K. If I go the other way, so I cross K minus J. AI minus K and AJ. And I cross I is J cross J, K cross K would be Z. So how do you do that? This. Assume I have a I, J, K. If I go from this side, they are positive. Ij would be K, Jk would be I, Ki would be J. If I go the other way, would be negative. So Ik would be negative J, Kj would be negative I, Ji would be negative K. You got it? So instead of memorizing any of this, if you remember these two, make it much easier. Now that we know this, now that we have that, what's that? Assume I have the A, is the AXI plus AYJ plus AZK, and the B is BXI plus BYJ plus BZK. Now, A cross B would be I, J, K, AX, AY, AZ, BX, BY, BZ. So, have a determinant before. So I'm gonna just put it how you're gonna calculate it, or you can just plug it in your calculator. Your calculator can solve what it is. So the A cross B, the first line is ijk, the second line is the first vector, the third line is the second vector. ijk, component of first vector, component of second vector. So remember how did we do that? So it says that I eliminate row and column, write whatever is left. Remember that? So it's gonna be A cross B. So I, it's gonna be I, eliminate row and column that it has it, and write it. So it's gonna be AY, AZ, BY, BZ. The next one, in the determinant, remember that we go plus minus. So if the first one is plus, the second one is gonna be, so if this is plus, the second one would be minus. So it's gonna be minus J. So eliminate the row and column that has a J and write the rest. So it's gonna be AX, AZ, BX, BZ, plus, minus, plus. So the next one is going to be plus K. Again, I eliminate the row and the column that has a K and write the rest. So it's going to be AX, AY, BX, BY. Agree up to here? So look at, we are going to do it by numbers, but you get it up to here or whatever. So how do you do the 2D determinant? The 2 by 2?
Was it
2 by 2.
AY BZ plus AZ BY? Something like that.
So it's going to be this time this minus this time this. So this minus this time this. This time this minus this time. So it's going to be the A, B is equal. So this is the I. Put it right. It's equal, so this one's plus AYBZ minus AZBY I minus AX BZ minus AZ BX J plus AX BY minus AY BX. Okay. So that's going to be the determinant. dot product. Any question? Any question? What the dot product? Next is gonna be the moment of force, or the moment in 3D. Can use it for 2D as well, but usually we use it for 3D. So in 2D, if I have a 2D condition, what was that? If there's a point O and there's a simple force F, and then there was a distance T, so the moment was F D, right? In this case, it rotates counterclockwise. I was rotating this. It rotates clockwise. Okay? Now in 3D, if I want to show it, it's like, if I have a, see how it's rotating to show it. So if I have a point here, there is a force in 3D. Try to draw it. And then it's gonna be, like, that's the force. And then from that point, I'm going to draw this. That's the R. That's the F. The M would be R cross F. That's the O. So, how do I show it? How can I show it? So it's going to be, it says I have two vectors. That's going to be R and F. R, F, like this. So the M is gonna be like that. From the first one to the second one, from the R to the F. So M is gonna be like this. So that's it. M about the O. So R is a position vector. So when I want to choose the R, where it should start, where it should end. Where the R should start, where the R should end.
Start at O and then F.
Start at the O, but where on the F?
Or it's perpendicular.
So the tangent.
Tangent. It can start, it should start on the O, but the good thing is that it can end anywhere on the line of action of the F. It doesn't matter where. At any point on the line of action of the F. So R starts at O and end on any point on line of action of force. So it can start, it should start at the O, but it can end anywhere on line of action. So if this is a force, O, no, sorry, this is a point O, and this is a force F. That R, so I'm going to draw the line of action for that force. So the R can start from here to here, that's R1, from here to here, R2, from here to here, R3, or at any other point. The M about point O would be R1 times F cross F. It would be equal to R2 cross F. It would be equal to R3 cross F. Any R, as long as it starts from the O and sits on line of action of the F, we are good. Got it? So when we want to find the R, when we are given the problem, we want to find the R. So the start point is fixed, should start from the O. But we can play with the end point. So we try to play with the end point, see which location is the easiest to calculate that vector. Just play a little with P0, probably it's easier for that, for one point compared to the other point, to work with that. Now, I have the R xi plus r in y direction j plus r in the z direction k. And the f in the x direction I plus f in the y direction j plus f in the z direction k. And you want to calculate the moment. So the moment would be r cross f. What was the first line of the determinant?
First line.
Determinant
JK.
ijk. So the first line is always ijk. The second line is the first vector, component of the first vector. So it's going to be rx, ry, rj, rz, and this second line, the third line will be component of the second force. So it's going to be fx, fy, fc. So similar to what we have, it's going to be plus I, rx, ry, fx, fy, minus j, rx, rz, sorry, it's fine, it's ry, rz, fy, fc, then the j is rx, rz, fx, fc, plus k, rx, ry, fx, fc. Don't forget that plus minus. I'm gonna write it with the rest. Remember that the first one is plus, the second one minus, the plus. So, but go ahead and write it so that the n r times f would be ry fz minus rz fy 5 plus minus rx fz minus rz fx j plus rx fc minus r. Rx fy minus ry fx and k. Oh. So that is going to be so that's the moment. This part is the moment about axis x. This part is the moment about axis y. This part is the moment about axis so basically this whatever is the assume this is our vector for the moment vector, so we find its component on the x, its component on the y, and its component on the z. So component of the moment along the z, component of the moment along the y, component of moment along the z, x, y, z. So that's how we calculate the moment in 3D. In case that we are going to have more than one force, similar to previous, so if we have the resultant moment similar to what we have previously, so moment of resultant what point O would be just add them all together. The sigma r plus m. Add all the r cross f together. Similar to what we had before, the principle of the moment. For 2D we can have, usually never use it for 3D, but we can have it also for 3D. So in case that I have a force and the point O so if I have a force F, and it's gonna be U and V, and we find its component along the U and V. And it's gonna be the R. It's the R. I also can write it like previously, like I said, the moment about point O is R cross F. Or I can do it as R cross FU plus R cross F. And it's a 3. So we have it in 2D, we did it in 2D. It's a 3D format or vector format. If you have a vector, break it into the component, calculate the moment for each component, add them together. Like the example we did at the beginning of the class. We break it into the x and y, then we calculate the moment for the x1, for the y1, then we add them together. It's a 3D format of that, or vector format of that. Usually we don't use it, but someone asked it, so what it is. You can break the force to its component and calculate moment for each component and then add